Hello everyone. Today we will start the third module and this is the 7th lecture of remote sensing for natural hazard studies, and today we will talk about the hyperspectral data acquisition and processing. So as usual, this lecture will be divided into two parts. So this is the first part. So I hope you remember this hyperspectral remote sensing. The basic definition was we should have the contiguous bands and the number of bands should be more and the bandwidth should be very narrow, right. So with that, what we do is we try to generate the spectra of each pixel. So each pixel of the acquired image has an associated spectrum. That means for each pixel, if this is the pixel or this is the pixel, we will have associated spectra, right. So this spectra will help you to analyze and gain the composition information about the target material. So here, considering this is one pixel and we have derived this spectra. So this is a hypothetical case where we are having this spectra, and this spectra will help you to gain the information about the target material based on their absorption position. So here it says distribution of electromagnetic radiation emitted or absorbed by a particular object, right. So whether it is emitted, reflected or absorbed, we can have this kind of spectral behavior of target material, and this we get because internal atomic structure and composition are the reason for absorption features. Because here if we have the target and this is the sensor, it is looking at this particular area, and with the fixed IFOV it is generating a pixel information. So the energy which is reflected, emitted or absorbed by this particular area or the pixel will be recorded, and we will have this kind of spectral behavior, right. So here it depends upon the material's composition and the internal atomic structure, how they will be behaving and how they will provide you the characteristic absorption feature, and that we are able to use or utilize to characterize them. So trough are the places where things are happening. I hope you remember my first example, that if we take the example of vegetation, and here this is basically your green band and our eyes are sensitive from here to here, right. This is 400 to 700 nanometer. So since our eyes have limited vision, so here this green color which is reflected from the target, it is getting detected by our eyes, right. But if we look at this IR region, NIR or SWIR, here you can see this reflectance is much more than this green. But since our eyes are not able to detect this wavelength, we see vegetation as green, right. But if our eyes are sensitive in this, we would have seen this vegetation in different color, right. So keeping this in mind, you can just try to understand if a particular wavelength is not interacting with the target, it is getting reflected. If it is interacting with the target, that means that is getting absorbed by the target. So this particular absorption features will give you more information compared to these, right, that this target is X, Y or Z. Here it is the example of quartz, right. So quartz has this kind of emissivity spectra, and remember this is a function of wavelength. Now when we talk about the imaging spectroscopy, to acquire the spectroscopic information over large area, and it has both the power of spectroscopy and imaging. So when we talk about the spectroscopy, it is instrument based which is capable of generating the spectra of given material, but it will not have the spatial distribution. So, it will not cover the large area, it will cover only a small portion of the sample that we do in XRD, XRF, ICP. So, everything works on the spectroscopy principle, right. So, here when we talk about the imaging spectroscopy, simultaneously we are measuring the spectroscopic information for a larger area, right. So, this imaging spectroscopy has both the power, it will generate the image and it will also generate the spectra, right. So, here you can see, if we take the example of this field spectroradiometer. So, this field spectroradiometer is capable of generating this kind of spectra. So, what we do is, with this kind of pointer, we place it over the sample, or we have different setup through which we will target or focus the fiber optic cable. This is here, you can see. So, this we will target, and this cable, it will have a IFOV and it will look at this particular area, right. So, it can be centimeter, meter, millimeter, depending upon the height of the instrument, or this is the target and this is the sensor. So, what is the height and the field of view, that will decide how much area you will capture in one spectra, right. This kind of measurement will provide you the spectra of the material in such a way, right. So, here you can see again we have some absorption position, some reflected area which is very high. So, which one we should consider? We should consider the absorption feature wherever we are getting the absorption positions, right. That will tell you about the material characteristic rather looking at this particular position. Now, this kind of instrument will help you to upscale the ground information to the satellite scale, because what happens if you generate an image, or if you generate a hyperspectral image like this, because of the uncertainties and the error introduced by the topography, by the atmosphere, by the instrument itself, you will not be able to prove that this particular behavior is purely because of the target, right. So, in that case what we do is, we have to rely on this kind of ground measurement. This instrument, we take it to the field and then we measure the spectra, and we consider this is the pure spectra of that particular target, right, which we covered in the field. And once we have this information from the field, right, what we do is, we try to correlate with the same pixel spectra of this image, and then we see how much matching is there, right. And based on that, we will be able to say that this is the accuracy of my satellite image result, which is produced by some processing steps, right. So, this kind of instrument will help you to upscale the ground information to the satellite scale. Please remember, this is very important. Whenever you go for hyperspectral data processing, you will have to have some ground measurement or some way to validate your result, otherwise you will not be able to justify your results are accurate or precise, right. So, here I hope you remember this is the basics. So, from here we are illuminating the target, and then from here the reflected emitted energies will received by the sensor, and this sensor will provide you this kind of spectra, and you will also have few bands that can be called hypercube or hyperspectral data, right. So, let us talk about the field spectroscopy. So, here we will talk about the spectroradiometers. So, spectroradiometer is an optical instrument that uses detector to measure the distribution of radiation in visible, near infrared and shortwave infrared wavelength regions, right. So, if you see, this is one type of spectroradiometer, this is another type of spectroradiometer, this is another type of spectroradiometer. Please remember, I am not advertising for any company, this is just for the example. I have put the photographs of these most popular spectroradiometer available in the market, but there are many such instruments are available. So, for example, how will you identify whether this instrument is capable of generating the data for your objective? That you need to check the data sheet, right. So, here for this particular instrument, this is designed by ASD. Wavelength range that is measured by this instrument is 350 to 2500 nanometer, and the spectral sampling, how frequently you are generating the data in wavelength, right. So, at every 1 nanometer you will have one measurement. So, remember 1 nanometer and you have 350 to 2500 nanometer, how many data points you will be generating across the wavelength, that you can calculate. Collection time, minimum time required to measure one spectra, that is 0.1 second per spectrum, and here we are using two different sets of detector. One is silicon photodiode, it works from 0.35 to 1 micrometer, and 2 Indian gallium arsenide, that is from 1 to 2.5 micrometer. So, these two detectors are used in this instrument to generate the data from 350 to 2500 nanometer, and the field of view is 25 degree, but such instrument comes with an option where you can change the field of view. So, it can also have 4 degree, 16 degree or 25 degree. So, this kind of additional attachment comes with this instrument, so that you can focus your target more precisely, right. So, these instruments are capable of measuring the spectral reflectance, spectral transmittance, spectral absorbance, spectral radiance and spectral irradiance. Now, why we are talking about these parameter in spectral domain? Because we are generating the information, let us say first spectroradiometer example. So, 350 to 2500 nanometer, that wavelength we are using to generate spectral reflectance, right. So, the first one is the reflectance. So, we have to have the radiance and irradiance, right. Remember, at every 1 nanometer you have one measurement for that spectroradiometer. So, the first measurement will be at 350, then you will have 351, 352, right, 353, like that you will have till 2500 nanometer. So, same way when we are measuring this radiance, you will have individual measurement across these wavelengths. When we are measuring the irradiance, we will have all these measurement. Then what we do is, we calculate the reflectance using this particular formula, and then you will have the spectral reflectance, right. So, this is why we are calling it spectral reflectance. In the same way, we will measure the transmittance, absorbance, radiance and irradiance that we have already discussed. So, all these measurements can be done with the spectroradiometer, which is available in the market. It can be ASD, GAR or any other company. So, remember, this is just for the example, I am referring their name, I am not validating or I am not advertising their instruments. Now, this is one thing which is very important, that is spectral panel. This spectral panel is used to measure the irradiance and as well as white reference, right. We will see why we need this in this spectroradiometer. So, remember I told you that if we have a satellite which is looking at a particular area, so with one detector it is generating one single pixel, right. So, this pixel when we are measuring from here, it is the reflected energy. So, we measure the radiance. Initially we measure dN value, then we convert to radiance, and then we should also have irradiance, right. Once you have the irradiance, then we calculate the reflectance, radiance by irradiance. So, here if same instrument we have and we can put it here over the ground focusing towards the sun, because sun is our source of light in this condition. So, this will provide you the irradiance, right. But this is not possible because these instruments which are sent to the space, they are different, and the same wavelength you can measure with different instrument, but different instrument will have different problems and advantages according to their detectors or the configuration. So, what we do is when we talk about the spectroradiometer, so this spectroradiometer, remember here this is the main instrument and this is the fiber optic cable which is allowing the energy to pass through this, which is coming from the surface or the target, which enters into this, and then through this fiber optic cable it goes to this main instrument, right. So, the light is falling on this, then it is entering into this, and then it is getting transferred from here to this instrument, right. And here this will measure depending upon what is your target, whether you are focusing towards the sun or whether you are focusing towards the surface, you will measure the radiance and irradiance, right. So, this is how we measure the radiance and irradiance. But when we try to focus towards the sun, what happens? Your instrument will get saturated, right. From sun, this is the incoming radiation. Most of the time it is getting saturated because this energy is too high to be handled by this particular instrument when we are directly focusing towards the sun or the source. So, what we do is we put this kind of panel which is a speculant panel. So, this is isotropic in nature. So, it has a property, whatever energy falls on this, it will be equally reflected in all the direction and it does not absorb, right. So, now if your instrument is here, right. So, this is looking at this particular portion of this panel. So, here you will have the irradiance measurement. So, when this kind of setup we refer, when we have a speculant panel on the ground which is reflecting the energy coming from the sun, right, and it is measured by the spectroradiometer, right. So, this is called downwelling radiance. So, this is also a radiance, but this is downwelling radiance. So, actually when we refer to downwelling radiance, this is your irradiance, right. So, downwelling radiance is your irradiance. Now, you remove this speculant panel, and then this particular sensor will focus on the ground, which is your target, and then you will measure your radiance. So, now you have both measurement, radiance and irradiance, and then you can calculate the reflectance. I hope this concept is clear. So, this kind of isotropic material is used to measure the downwelling radiance, which is nothing but the irradiance, only the style of measurement is different. Instead of focusing towards the sun, we are putting it on the ground and then we are measuring the radiance, and actually the property of this particular panel is it reflects equal amount of energy in all the direction. So, this will give you the incoming radiation, right, and this is called irradiance. But when we refer to a speculant panel to measure the irradiance, we call it downwelling radiance. Please remember this is very important. Now, factors that affect the spectral measurement. So, atmospheric characteristic and stability, because whenever we go for the measurement, when we have a spectroradiometer with us and when we go to the field to measure the spectra, we try to see what are the parameters which can influence the measurement. So, the atmospheric characteristic is one of them, because every moment atmospheric characteristic is changing, clouds are moving from one place to another place. So, the irradiance which is coming from the sun will be changing very frequently, right, and the wind speed, that will also affect your measurement. Sampling, viewing and illumination geometry. So, how you are looking at the ground with your spectroradiometer, whether it is nadir or whether it is off nadir, how you are going to utilize this information, whether you are going to upscale this information to satellite scale. If a satellite has 5 degree off nadir measurement, then it is suggested that you should also have 5 degree off nadir measurement at the field level, right. Then only you will be able to correlate these two values. So, one value coming from satellite, one value coming from the spectroradiometer, and then you will be able to correlate them. Source of illumination means what is your source, whether it is sun or whether it is a tungsten halogen lamp which is characterized and you have full characteristic of that particular lamp. So, that can be seen here. Instrument field of view is basically how much area spectroradiometer is covering to generate one value, right. So, because spectroradiometer is looking at this particular area at this height, right, this IFOV is fixed, let us say this is 25 degree and this is 1 meter. You can easily calculate what will be the footprint on the ground. Now, once you have this information, whether you want to cover a part of the sample, let us say this is an exposed rock and you want to measure this particular portion of this sample. So, you need to adjust your height because IFOV is fixed. So, you need to adjust your height so that you will be actually covering this particular portion of this sample, right, in the field. So, this is very important to check how much area my instrument is covering and what is my target sample and how you are going to correlate with the satellite measurement. Now, instrument scanning time. So, remember I told you that one of the instrument has 0.1 second per spectra. So, if I move my hand very frequently and if it is less than 0.1 second, my spectra will not be captured perfectly. So, we need to hold the fiber optic cable for minimum 0.1 second at that particular position, so that it will actually generate the spectral behavior of that particular sample. Next is sample characteristic, whether it is rough or whether it is a very smooth surface. Depending upon that, you will have to adjust the measurement. Then wind speed, then comes the steps involved in the measurement, right. So, I told you that previously spectral panel we are going to use in the field for the spectroradiometer. So, here first thing we need to measure is the dark current. So, dark current, then next is the white reference and then target spectra, right. So, this white reference is basically your irradiance, which is nothing but the downwelling radiance, right, and this target spectra is basically your radiance. So, when you have these two measurement, you can calculate the reflectance, right. But what is this dark current? This dark current is something related to the instrument. Dark current refers to the current generated within a detector in the absence of any external photons. So, what happens if this is the spectroradiometer, this is the slit from where you have the fiber optic cable connected, which is having a field of view of 25 degree and it is looking at the ground, right. So, here you have different detectors, remember the silicon and Indian gallium arsenide that was there. So, they are arranged in such a way when light enters here, they will be sensed by these detectors, right. So, when we close this slit, let us say we have closed this. So, when we close this, these instruments are turned on, it is measuring the signal, but without any external energy, this particular detector we will see whether it is getting any kind of energy or photons. So, in general, when you turn on any electronic device, the instrument get heated, and once you are having the heat generation, you will have the photons, right. So, that will be the additional information which is coming from the sensor itself. So, that we need to subtract from the measurement of irradiance and radiance, right. So, that is why this dark current measurement is very, very important. It measures the radiation or the energy which is generated by the detector itself in the absence of any external photons, right. Now comes the white reference. A material with approximately 100% reflectance across the entire spectrum is called a white reference panel or white reference standard. So, this white reference standard, so I showed you one example here. So, you have this spectral panel, this is also called as white reference panel, right. So, this white reference is used to measure the downwelling radiance, which is nothing but the irradiance. Now, my instrument is ready to measure the radiance, and once you have these two measurements, you can have the reflectance, which is radiance coming from here and irradiance, which we use the white reference panel and we call it downwelling radiance, which is coming from the white reference, and then we will have the spectral reflectance. I hope this is clear. So, imaging spectrometers acquires images in a large number, narrow, typically 0.01 to 0.02 micrometer in width, that is your bandwidth, right. So, I told you 10 to 20 nanometer is allowed when we talk about the hyperspectral remote sensing, and they should be contiguous in nature. That means, they should be adjacent to each other. Between two bands there should not be any gap in the wavelength. So, when you are having this kind of measurement, you will be calling them hyperspectral remote sensing or imaging spectroscopy, that both are same, right. So, here we are generating these bands, and then for each pixel you will have this kind of measurement, and here the characteristic absorption feature that will be studied, and we will call it a material X, Y or Z, right. So, this is very important. So, spectroscopy, when we have only this kind of measurement which is coming from the spectroradiometer, right. But when we talk about the satellite images where we have the hyperspectral remote sensing configuration, we call it imaging spectroscopy or hyperspectral remote sensing. I hope the difference between the spectroscopy, imaging spectroscopy and hyperspectral remote sensing is clear. So, this is different. Here you have only one spectral measurement, and these two are same, imaging spectroscopy and hyperspectral, and here you have images like this, and these images pixel will have this kind of information, right. So, this is imaging spectroscopy. So, we will continue this course in the next lecture. So, with this I am stopping here. Thank you very much.